Okay, so for the next couple days, we're going to be solving trig equations. So we're going to introduce it today. We'll really work on it on Tuesday. Remember, it's a 3-day weekend. And then Wednesday, we'll do an activity to practice and really hone our skills. Now, if I asked you the sine of x equals 1/2, solve for x, what would you maybe tell me? 5 or 6? Would you have anything else for me? 5, 5 or 6? Anything else? 30 degrees. Okay, I want you to think about two things. Think about what the graph of sine looks like. Can you picture it? Does it only go from 0 to pi? Or 2 pi, excuse me? Where does it go? It goes forever, right? It's an infinitely long graph. So if I think about all the places this graph is 1/2, yes, it happens at pi over 6, but then it happens 2 pi later. And then it happens 2 pi later. And then it happens 2 pi later. Right? Would you agree? And we can go the other way. Here it happens at pi over 6. But then if we go backwards 1 full period, it happens again. If we go backwards 1 full period, it happens again. So how many solutions technically are there to this equation? Infinite. Now, you're not going to write infinitely many solutions because we actually can describe what those infinitely many solutions look like. Okay? Now this 2 pi, where's that 2 pi coming from? Okay, that's the whole period of the graph. Kaden, let's think about the unit circle. Okay. There are 2 places on the unit circle where the sine is 1/2. It happens at pi over 6, and it happens at 5 pi over 6. But then we can rotate around the unit circle, 2 pi, Kaden, over and over and over again, and we have an infinite number of coterminal angles where the sine is 1/2. Okay? So yes, we need to remember our unit circle angles and pick out the places where sine is 1/2, but then we also have to notate that it happens every period. Okay? Graphically, if we think about it, every period we have that same thing happen over and over and over. And the same is going to be true for any cosine graph, any tangent graph, secant, cotangent. These are all what we call periodic functions, where there's a period that occurs over and over and over and over again. So we get the solution occurring every time within the period. So this is going to be our process. I want you to write these steps down. Okay? We are mixing together our knowledge of algebra with our knowledge of trig. Okay? So we're not going to have a linear equation, x plus 1 equals 2. We're going to have a linear equation potentially in the form of sine of x plus 1 equals 2. Okay? So if you have a trig equation that's a linear trig equation, get the trig equation by itself. Okay, sine of x equals 1/2. The trig equation is by itself. So add or subtract anything connected to it, divide anything out that's connected to it, and then we can look at where the trig function is equal to a particular number. Okay, now linear equations. So pretty simple, okay? They're not all going to be linear. So if it's not linear, you may need to consider setting your equation equal to 0 so that you can factor. This is more something we're going to work with on Tuesday. Okay? Today I want to focus on the linear types. But we'll work on factoring to solve on Tuesday. It is possible, which is why we do it in this chapter, it is possible that you need trig identities to help you. Okay, we're going to look at an example on Tuesday where there's both a sine squared and a cosine squared in the equation, along with maybe another function. Okay, what is going to be the most helpful for us to solve? Okay, so don't feel like you need to use trig identities every time, because you will not. But it could be something we need to use if we get stuck. Okay. But when you actually get to a point where you're ready to tell me angles, you need to write your solutions in this manner. You need to give me the angle, that's the solution, plus whatever the period is times n. I'm going to let you write that down, and then I'll talk about what that means. So you're going to have one of the 6 trig equations as a part of your problem. And when you get that isolated to equal some number, you're going to identify an angle. Okay? For example, we had the sine of x equals 1/2. Okay? So first you're going to identify the angles in which that occurs. So when I asked you, you guys were telling me, well, pi over 6 and 5 pi over 6 are the 2 places where the sine is 1/2. Okay? But then you need to express that it happens over and over and over again. So we're going to think about, well, what's the period of sine of x? Okay? The period of our sine graph is 2 pi. So you're going to add the period times n to express that those solutions happen every period along the graph. Every 2 pi, those same solutions are going to occur. Instead of you having to list pi over 6 and 13 pi over 6 and 25 pi over 6, that would be completely obnoxious, right? So this is a way for us to express an infinite number of solutions to where we know where they are. All right, so I have 3 examples that I think we can get through today. And then your homework assignment, super short, right? 5 problems. Thank you. So 5 problems, and they all are going to look fairly similar to what we're going to do here. So go ahead and write this one down. Okay, so we need to isolate our trig function, and since our trig function is sine, we need to get sine by itself. Okay, what's one thing that we could do?
Could we subtract sine over? Or could we subtract?
Or what?
Radical 2 over?
Okay, we can do a combination of the two. Okay. I will take both of your suggestions. Maybe we could take this sine of x and combine it with this one over here, and then, like you said, subtract the negative, this radical 2 over. Okay, so let's move this radical, or this sine of x over to this side. So we would have 2 sine of x plus radical 2 equals 0. Okay, then we could subtract radical 2 like you suggested. And to get sine of x completely by itself, we could then divide by 2. Okay, so we're using our Algebra 1 skills here, right? We solved the linear equation by getting sine of x by itself. Well, now we need to solve by x by using our trig knowledge, okay? So once you get a trig function equals a number, we can now prepare to write our solutions. So on your paper, write down the 2 places on the unit circle where the sign is negative radical 2 over 2. Eli, what'd you write down?
5 pi over 4.
Is that it?
Yeah, 7 pi over 4.
And 7 pi over 4. So we have 5 pi over 4 and 7 pi over 4. And then the period of sine is 2 pi, so we're going to add plus 2 pi in. Okay. So if we're talking about sine, cosine, secant, and cosecant, your period is going to be 2 pi. However, tangent and cotangent, it would be what? What is the period of tangent? Remember? What's the period of tangent? It's pi. Okay, so tangent and cotangent would have the periods of pi, and that would be the time where we would put something different here. Okay. We'll also look at what happens if there's like a horizontal stretch or shrink where our period wouldn't be the standard, but we'll talk about that on Tuesday. And you won't actually have to recalculate the period. We'll just do algebra to adjust our answers. So what you need to worry about in terms of these numbers right here, if it's sine or cosine or their reciprocals, 2 pi is the period. If it's tangent or its reciprocal, pi is your period. Okay, so if you need to make a note to yourself, the period of tangent is pi, go ahead and do that. And then n is just representing any integer. I could plug in an integer for n, and it would describe a solution somewhere on the curve. Okay. Go and write this one down. This one's a little different in the fact that there's a square in there, but it's really not going to affect our process except for one thing, okay? We can still add over that 1. And divide by 4. Since cosine squared is the only thing in there, we can isolate cosine squared. Now, if there was a cosine squared and a cosine to the first power, then we would have to look at our factoring techniques. But since cosine squared is the only thing in there, we can isolate cosine squared. Then we could do what?
Square root.
We could square root both sides. Okay? Please remember that when you square root both sides, we have to account for the positive and negative solutions. If we square a negative number, we get a positive. If we square a positive number, we get a positive. So when we're working through an algebraic equation and we square root both sides, bless you, we need to account for plus or minus. Okay? Square root of 3/4. What's the square root of 3? Well, square root of 3, but what's the square root of 4? Hey, that's nice. We recognize that number, don't we? Okay? So what we need to do, we're going to have 4 solutions. We are going to have 2 places where the cosine is radical 3 over 2, and we are going to have 2 places where the cosine is negative radical 3 over 2. Okay. Gracie, give me one of the angles. Which one? Pi over 6? Okay, pi over 6, which means another angle would be 5 pi over 6. And another angle would be 7 pi over 6 and 11 pi over 6. We have all the pi over 6 angles. Okay? And then since cosine has a period of 2 pi, we can add 2 pi n to it. Okay. Now, I need to make you aware of something that you're going to encounter if you check your answers in the back of the book. Okay. In this problem, our answers were all 4 of the pi over 6 angles. How far apart are pi over 6 and 7 pi over 6? They're pi apart, aren't they? So what the back of the book is going to do, they're going to say, hey, I can combine this to just be pi over 6 plus pi n. And then they're going to look at these. How far apart are 5 pi over 6 and 11 pi over 6? They're pi apart. So they're going to say, hey, I can write this as 5 pi over 6 plus pi n. And I only have to write 2 solutions instead of 4. Okay? I am perfectly happy with those 4 red solutions. Okay? That is probably what I'll look for when I grade your work. However, when you check your answers, I don't want you to be alarmed when this happens, when they take 4 solutions and they consolidate it to just 2. Okay? But am I happy with the red? I'm happy with the red. Okay. One more example. Okay. What I'd like you to do, that's not the, nope. Sorry. I'll have to write it. I thought I had a slide for it, but I don't. All right, 3 cotangent x minus radical 3 equals 0. I'm going to give you 2 minutes to see what you can do with this problem without me. Yes, you can use the help of your peers if you like, but I want you to see what you can do with this problem without me, and then we'll talk about it. Remember when I said you're going to have to know your unit circle in chapter 5 and 6? Yep. This is why. That's a good idea. Brecken, what was your first step?
I added radical 3.
Added radical 3. Mia, what'd you do after that? So we have the cotangent of x equals radical 3 over 3. On the unit circle, there are 2 places where the cotangent is radical 3 over 3. What are they? Let's think about it. Is 1/2 over radical 3 over 2 or radical 3 over 2 divided by 1/2 going to get us that? Which one, the first or the second? This one, right? So which coordinate, x divided by y, is going to give us
It's the
pi over 3 angle. So pi over 3, and then cotangent's also positive in the third quadrant. So 4 pi over 3. And then remember the cotangent has a period of pi. Jacob, how far apart are pi over 3 and 4 pi over 3? Oh, they're pi apart? And our period is pi? Okay, so technically, this one solution includes this right here. Do you see what I mean by that? These are pi apart, so by saying pi over 3 plus pi n, that would include this value right here. So technically it's redundant to give me the 4 pi over 3 plus pi n, and that's going to happen every time you have a tangent or cotangent equation. Will I be upset that you give me both? Not at all. I don't mind you being redundant in this case. Just know that when you check your answers, they're only going to have the first one. But if you put both of them, I'm not upset. Okay? All right, so you have 5 problems for your homework. Okay? Check your answers. They should be fairly straightforward, much like the ones we did up here. If you did not grab your Math Valentine, you may do that at this time. Or if you don't want one, that's fine too. Yeah.